Welcome to the class of high performance computing for scientists and engineers, and we are discussing the fourth module of this class, which is GPU computing. Today we'll discuss about matrix multiplications in CUDA. In last few lectures over last couple of weeks, we are learning about different nuances of CUDA programming. We looked into how to parallelize a section for in GPU to run in GPUs using CUDA, how to take care of memory management in CUDA, what are different off-chip and on-chip memories, and how to utilize these memories efficiently in CUDA programming. And now with that background, we'll see examples which are very much related with scientific computing, and these are matrix multiplication operations. We understand that dealing with large scientific or engineering problems often require utilizing matrices, doing matrix vector product, matrix multiplications, and we'll see how CUDA can be efficiently used for that. So in this class we'll see that how using the thread and block ID we can point to different locations of main data, because we are using a single instruction multiple data model. So essentially same instructions will be ran over different locations of the data, and how thread and block ID can be utilized for that. We'll see examples on matrix vector product. We'll see the programs on matrix product using CUDA to run on GPUs. We'll see how tiling, if you remember, we have discussed about matrix blocks or matrix tiles when discussing about matrix products while discussing OpenMP programming. So how this tiling and how utilization of shared memory can improve the performance of matrix products. There are certain complicated memory access in matrix product, cache unfriendliness can be there, which has to be taken care of. And we'll also see some examples related with matrix solvers and how the performances are. Well, so if we look into a CUDA kernel, when it is executed, it launches a number of threads, and these threads are launched as a grid. Inside each grid there are multiple blocks, and these blocks are composed of number of threads. So kernel launch is essentially a single instruction multiple thread model, or single instruction multiple data model parallelization using multiple threads. And kernel function is executed on what are the number of threads. So the kernel function is executed on grid size into block size number of time in that many threads. So if a kernel is launched, grid size is the number of blocks and block size is the number of threads in each block. So total number of threads will be grid size into block size, because each block has same number of threads. So that will be the total number of thread launching when a kernel is launched, and this information is available in the execution kernel. What is the block size and grid size? Programmer has to specify a block size and a grid size, and in the execution kernel, which is given by the variables grid size and block size when you call the kernel. And then these variables are of type dim3, so you can put 3 integers in grid size and say that this is the number of blocks in x, y and z direction. Similarly, you can use because there is a dim3 variable, 3 integer in block size, and say that these many are the number of threads in each block in x, y, z direction. So in total you can launch a large number of threads, and you can find out what is the total dimension of block when the code is being executed. You are say you are specifying grid size and block size as dim3 variables, but when you are inside the kernel might need to know what is the total number of blocks and what are the total number of threads inside a block, etc., which can be found out. The block dimension, that is the total number of threads inside a block, can be found out these variables. And a thread also required to know its identity. What is the particular specific number of the thread? Now if we think of MPI and OpenMP program, there are function calls by which a thread or a processor knows its rank or identity, and in GPUs, because there will be large number of threads already in a GPU kernel, if you call functions to identify the number of threads, that will add to high overhead. So there are some automatic variables which are block id x.x, block id x.y and block id x.z, which gives the local ID of the block. What is the ID of this block in XYZ? In the grid there are many blocks, and this is a three-dimensional arrangement. So when you look into this variable, it will tell you about the coordinate of the block or the location of the block inside the grid. Similarly, if you have to find the thread ID inside a particular block, you will get thread id x.x, thread id x.y, thread id x.z. These are C++ structures, like C++ structures. But this thread ID is the local thread ID, is the ID of the thread within a particular block, and in many times it might be required for one to know about the global thread ID. That means in, say, a block number P, there is a thread number Q. So what is the global number of threads? How many threads have already been passed before that? What considering the blocks which are counted before this block, what becomes a global ID of this thread? And we'll see when this will be important in a while. It may be important to find global ID of the thread for some problems. If we look into a matrix addition problem, when this global ID can be important, we'll see. And what we are doing here, we are adding two matrices. If we see, when we have launched the kernel, the number of blocks, total number of blocks inside the grid is 1, grid size is 1. So there is only one block. Inside one block there are n into n threads, n in x direction, n in y direction. So the thread ID inside that block will have two coordinate components, one is its x coordinate, another is one coordinate. Now when we call the kernel, we call the kernel function number of blocks, which is 1, threads plus block, because there is a dim3 variable, so it will take n into 1, and the input parameters. Now when the kernel function is called, it will do take matrix A, take matrix B, the output will be matrix C. So each element of matrix A will be added to corresponding element of matrix B, and the output will be an element of matrix C. How is it doing that? It is identifying the location of an element in matrix A or B or C by the thread ID. So thread ID in x direction. So if I am looking in a particular thread, this thread is taking one variable, one element of the matrix A, taking a corresponding variable of matrix B, one element of matrix A, taking a corresponding element of matrix B, and adding them and getting the corresponding element of matrix C. And this is being done by all the threads simultaneously. So which element a thread will pick up, that if you look into this code, that is found out by the coordinate of the threads. So inside the matrix, the element that is being operated by a thread has a index or has indices same as the indexes of the thread or the coordinates of the thread. So far so good. This is simple in a sense that each thread will do same operation. One thread will pick up one particular location of matrix A, similar corresponding location of matrix B, add these two variables, put in the corresponding location of matrix C. So xid of the thread points to the matrix row, yid of the thread points to the matrix column, and we get the product. Thread ID is used to point to the memory location which will be accessed by the particular thread. Now this is simply obtained here because we have launched only one block. Because we have launched only one block, the thread ID x and thread ID y can directly correspond to the element location or the indices of the matrix. Each thread can be directly mapped to each one element of the matrix. Well, so we can go ahead with one block. I mean, within a block there can be large number of threads which can be operated, so we can go ahead with one block. But if we now think of in terms of scheduling of the blocks, each block will go to one streaming multiprocessor. Inside one streaming multiprocessor, at one go, one warp of threads will be active. That means 32 threads will be active. So even we are launching large number of threads, say we are operating over 10 to the power 6 into 10 to the power 6 matrix. So we are launching 10 to the power 6 into 10 to the power 6 threads, but we are getting a parallelism only by the factor 32, because at one go only 32 threads are active. So we are not getting the right scalability. Therefore, if we are working on a V100 which has 80 streaming multiprocessors, we can think of at least 80 blocks. As a matter of fact, we run more than 80 blocks. So all the streaming multiprocessors are working together, and we are getting parallelism not only for the 32 threads in the warp, but also multiple blocks are active, multiple streaming processors are active, and all they add to the scalability. So you need to launch number of blocks. And I think I'm clear that if we run in one block, we'll get less scalability. We have to learn number of blocks, and we have seen last class that what is the optimum block size, that depends on a multiple of warp. That also has an effect on the performance. If you just keep on increasing the block size, even by multiples of warp, you may not get the right performance. There is an optimum block size depending on the memory utilization of the program. So we need to launch this kernel in multiple number of blocks. We need to have multiple number of blocks. Therefore, we cannot just pick up one block and say that its XID will correspond to the particular location of the thread. We need to use the global IDs of the threads. We have to consider that it's like multiple arrangement of threads are there. We have to count that what is the global XID, we have to count what is the global YID, and point the thread accordingly. So as a single thread is launched, local ID and global ID is same, but when multiple threads will be launched, they will be different. We have to take care of that. And this gives us the issue that my threads will be utilized also to point to the memory location. I will not use any other table or any other pointer to point to the memory location. The thread IDs are the pointers for the memory location. Each thread will do small amount of work. All the threads will simultaneously carry the work, therefore a large problem can be addressed. This is precisely a single instruction multiple thread model or single instruction multiple data model. Here we have large number of threads, and each thread is pointing to one location of the matrix, and therefore at a go the large matrix problem is solved. So if we have only one block, we can use the thread ID x as the x coordinate, thread ID y as the y coordinate, and locate a location of the matrix. If we have a general two-dimensional grid, we can extend it for three-dimensional also. You need to think of the thread algebra there. We have to use that thread ID x is the local thread ID, block ID x is the ID of the block, and block dim x is the dimension of the blocks in x direction. That means in x direction total each block has that many number of threads in each direction. Block IDs, thread IDs, everything start from 0 to the number of threads minus 1. So if a block has a local ID, if a block has a ID block ID x dot x in x direction, there has been 0 to block ID x dot x blocks before that, 0 to block ID x minus x blocks before that. So there are total block ID x dot x blocks which have passed before that. So each block has block dim dot x threads in x direction. So total number of threads in x direction will be their multiple, and then we add the local thread ID. Similarly in x direction, similarly in y ID, we do that and we find out the global thread ID using this. Global ID of the thread is obtained from the local thread ID, local block ID, and block size. Using these three information, whatever the block arrangement be 2D, 3D, we can find out the global thread ID and local thread ID. In certain cases there can be some more complications, but I mean using simple algebra that can be found out. And now we will look into a multi-block matrix vector product, and this is done by one of the programs that I will show is written by one of my summer interns, Mr. Dilip Subbiyan, who is a BTech from Shiv Nadar University. So we think of a matrix vector product. What is in a matrix vector product? A matrix row will be chosen that will be multiplied with the vector as a dot product. The corresponding column element will be multiplied with the corresponding row element of the vector, and we will get one row element of the matrix vector product. So we can see that the matrix D is multiplied with vector R. Now while looking into this product, this is a serial subroutine, this is a simple C code. One thing we can see that this matrix, instead of D being a matrix, a 2D matrix, it has been put into a vector order. So we have some way coalesce the memory access. Instead of writing the matrix, so we have this matrix. Instead of taking these matrices in this order 1 1, 1 2, 1 3, we have coalesced the entire matrix into an 1D array. So 1 2 3 4 5 6 so on. So the entire matrix is coalesced into an 1D array, and that's why row I and column j is written as n into I plus jth element. So there has been I rows and j columns there, and that is multiplied with the jth row of the vector. So the matrix is put into an 1D array for coalesced access. Why coalesced access is important? If we go back to the fundamental concepts of CUDA programming, from reading from the device name to the GPU codes require a coalesced access, and that is a cache friendly access also. So that is why we try to put the matrix in a coalesced access, that gives us better performance. And then when we write this programming GPU, instead of doing this in a through a function, we call a kernel MVM, and this kernel takes what is the block size is u, n is the total size of the n by n is the matrix size, the order of the matrix, a is the input matrix, x is the input vector, b is the product, and we can find b is equal to, from each location of b starts with, each location of b is initialized as 0, and then b is equal to b into the corresponding element of a into the corresponding element of matrix x. Well, another thing what we can see here, that we are finding out the global locations of I and j where the thread should point by block idx into block dim y into thread id, block idx into block dim x into thread id. So we are utilizing the global locations. We are also, because we have coalesced the memory access, see we are operating for over an index int. This index tells us about the coalesce, this index gives us a coalesce of the memory for the vector, and we are accessing the memory in a coalesced manner, and this int into n is the total number of elements. This is from the row index, it finds out total number of elements which is covered in the previous rows and goes to the particular row. The previous rows, it covers the previous row and looks into the location and the particular column of that row. So that's why we are using a coalesced memory access here. A coalesced global memory access pattern is followed, and this gives us better speed up. We can see that for 1280 matrix, CPU takes 0.44 seconds and GPU takes 0.38 seconds, and that's not very high speed up. Why? Because the computing is small. 1280 by 1280 is a small matrix problem, small matrix vector multiplication, and you are doing it only once, so speed up is not substantial at this case. Also, you need to copy the entire matrix, entire A matrix and vector, and from CPU to GPU, and then copy it back from GPU to CPU, that is the product. So it takes a large time. In case if you have a large matrix, then you get better advantages of parallelization, and we have seen that. Well, so one very important thing is that when we are looking into matrix vector pattern, a coalesced global memory access pattern is followed, and this index I and D is introduced for that. We are, instead of considering the matrices as 2D matrices, we are coalescing them into a single row and doing the operations based on that. This is extremely important to note here. In a matrix product, as we can see, when we think of a matrix product in CPU, it is each location of the we take a row of the matrix, a left hand side matrix, a column of the right hand side matrix, and take a dot product between them and make them the corresponding element of the product matrix. Now, when we look into the CUDA kernel, we would do essentially same thing. The local IDs, each thread points to one particular element of the product matrix, not on the left and right matrix, because in the multiplier and multiplied matrices, it will go over the entire row and entire column and make dot product. So it looks into a particular row of the multiplier matrix A, the threads x coordinate, the threads y coordinate, looks into particular column of the right multiplier matrix B, and the thread itself also looks into I and j, or the thread ID x and thread ID x y looks into particular row column location of the product matrix CD. So these matrices CD, AD, BD, because they have been copied from the host to device. Host matrices are ABC, and these matrices are AD, BD, CD. And this addition is done over all the elements this is dot product over all the elements in a particular row and column. Well, now what we can see, we have coalesced the memories. Instead of 2D matrices, we are considering them as 3D matrices and writing it to the particular location which is given by the global thread IDs. Now, there are few observations. There is a large number of memory access. In each row operation, it accesses memory from of the entire. For finding out one element in CD, memory of access is done for the entire row of A and entire row of B. So, if n is a large number, say we are talking about, we do typically HPC GPU computing because we have large matrices. So, we are talking about million by million matrix. So, for finding out one element in C matrix, I have to go for 1 million elements in A and 1 million elements in the column of 1 million elements in the row of A and 1 million elements in the column of B. So, large number of memory accesses are required, 2 million memory accesses required, and we will get 1 million operation by adding them. CGMA ratio is very bad, but as we have large number of memory accesses, it will be a slower process. However, for memory access, we avoid the reduction of bandwidth by utilizing cache, and what cache does, it prefetches some of the memory elements in the contiguous location. But here what we can see, because this is its row, A's row is multiplied with B's column, in A from K0 to N the memory is contiguous, but in B memory is not contiguous because it is N into 0, it is multiplied with N into K, it is looking into the column elements, memory is arranged along the row. So, either we have to store it as transpose of B, which is possible, else there will be a problem. So, what we see here, that this access, the way we are accessing BD is a cache unfriendly access pattern, and because we have to every time read from the global memory or take from the device RAM global memory and bring it to the CUDA cores, and many memory readings are required, it will be a cache, as cache issue is there, effective bandwidth will be low, it will be a slower process. So, utilizing shared memory might help us, and utilizing tiling, we have seen it earlier that if we consider blocks of the matrices and do the multiplications only within this block, we can use many of the cached variables, and that also can help. So, using shared memory and tiling can help us in terms of memory access and improve the performance. This particular program will have some performance issue. This particular program will have some performance issue. So, we look into in NVIDIA CUDA programming guide, the example is given. So, when you do multiplication in between two matrices, you read the entire row of one matrix, you read the entire column of one matrix, and only get one product here. Instead, if you take a block of or a tile of numbers here, and if you take a tile of numbers here, you first multiply them, get the products here. Again, this product is not final one, so you have to take another block here, another tile here. I will not use block here, block makes a different sense. You take another tile here, multiply them and write it back here. So this into this will give me some products in this particular operation. Look, this into this will also give me some products here, this into this also give me some products here, this block into this block will also point to this particular row. So you have to go over loops of tiles and then you can get the product here. So what is the advantage? Advantage is that once you read this entire block, all the products can be done here. You do not need to read the memory values. What means that when you are reading from the global memory, so you do not need to read it again and again. Also, as you are considering a small tile in both A and B matrix, the memory of these tiles might be small enough so that they can directly fit into the shared memory. So, and once something is read in the shared memory, it will remain in the shared memory unless you overwrite it. So one verb can read it, but other verbs also can utilize it. So read one tile of data from matrix A, read one tile of data from matrix B, put them into the shared memory, do all the multiplications required for matrix multiplication for getting the product matrix in between them, write in product matrix C. Again write another tile from matrix B. You may utilize this tile which is already in matrix A and do the products and add with the product in the product matrix location. In that way, and different tiles can be allocated to different threads, and that way you can get better performance. And we will see an example. So what we are doing, we are taking one tile of matrix A, putting into shared memory. You are taking one times, so this is here we are doing m into n is equal to p, one tile of matrix M and putting it into shared memory and doing the multiplication, putting them here. Then we are doing multiplication among all the blocks and putting it here. Then we will take another block here and maybe another block here, and some element will again come here. So we will keep on adding these elements. So the program looks like you identify the global thread ID, get the block ID, consider the local thread ID also, and using the use a shared memory variable. In the shared memory, you basically look into the thread ID, local thread ID in that particular block, and inside the shared memory, now this shared memory is only on a particular block, shared memory has no scope outside the block. So the shared memory variables you use using the local ID, and use the global ID, this is your global ID, use this global ID for fetching data from the global memory, put it into the shared memory and do multiple tiles till it finishes all the rows in the of the matrix, do multiple tiles for that particular block and keep adding on the global memory itself. So these memory accesses are local memory or shared memory access. Shared memory is a small memory unit, so you every entire memory is something like cache. Entire memory is directly readable using the shared memory banks, etc. So you don't need to think about coalescing the memory. The cache friendly access which might be required for larger matrices, but shared memory is here we are discussing only 16 by 16. It's few kilobyte, 6492 kilobyte as the maximum space. So you don't need to coalesce the memory access here, but the device memory or the global memory which you are accessing must be coalesced. And so non-coalesced access is used for shared memory as the size is small and bandwidth is high. For 1280 by 1280 matrix, sequential code takes 214 seconds. This optimized code takes 6.38 seconds. So near 30 times, more than 30 times speed up has been obtained using the GPU card here. And as we keep on why the speed up is more than matrix vector product? Because first is that we are using this optimization based on shared memory and tiling, and also the total computation is quite large here. In matrix vector product, total computation is small, only getting one row of the product matrix compared to this. Right here the product that was of the order of n, here the computation is of the order of n squared, it has large computing. We look into matrix solvers. These are very important in scientific computing calculations, and we look into conjugate gradient, biconjugate gradient and Jacobi solvers. If we look into all these solvers, these solvers are the maximum costly part or compute heavy part inside this solver is matrix vector product. So we have parallelized the matrix vector product here. Now matrix vector is not as costly as compared to matrix. The important thing is that these are iterative solvers, so these matrix vector products are required again and again. However, matrices remain the same, so you do not need to copy the matrix many times from host to device. So copying the matrix is done only once, but the copied matrix which is lying on the GPU device is operated again and again for matrix vector product, and large number of iterations are done. And if we see a Xeon 2650 versus a P100 speed, if we keep on increasing the matrix size, say 40,000 by 40,000 in a conjugate symmetric matrix, we get near 90 times speed up. For BiCG also we get high speed up, and as we increase BiCG, and this is done for this is near 30 times speed up because the matrix size is small. As we increase the number of rows in the matrix, the speed up is more. So these are for unstructured non-symmetric matrix, and conjugate gradient is for symmetric matrix. As we increase the speed up size, the speed up increases here also. So that is one observation also. This follows the basics of parallel computing performance, that as we are increasing the problem, the speed up is better. And for that, to get that, we in GPU there is a challenge of memory access, so you have to be very cautious while looking into the memory access. So matrix solvers and matrix vector matrix products are very important in scientific computing, but we can see that if we write the GPU codes efficiently, we can get very good speed up, and this speed up is comparable to a even more than a large CPU based infrastructure. You need many more racks of CPU, a big room with air conditioning to get something like what we are getting, around 90 times speed up. You need maybe hundreds of CPUs there, but a simple single GPU card, if the CUDA program is tuned properly, can give you similar or better performance. Well, mainly I have used CUDA C programming guide and CUDA C best practice guide. These are very important in case you try to develop your own CUDA program. For this lecture, we have looked into basic thread algebra for vector and matrix operations, shown parallelization of matrix operation, and optimization using shared memory and what is called tiling here, and performance of parallel matrix solvers are also presented. Thank you.